All right, guys, we're back to talk about the next major component of Chapter 3, and that is intermolecular forces. All right, now intermolecular forces, they're really nothing new to you, right? You guys talked about them in general chemistry and probably high school as well. We're going to do a review of them because we're going to see there's particular intermolecular forces that are going to be especially important to us and into the physical properties, certain physical properties of organic compounds. All right. Now, just to review, an intermolecular force is anything or any type of sort of attraction that occurs between molecules, but it's not enough of an attraction to make a full covalent bond. So you're not actually making a permanent bond. You're just sort of, almost for lack of a better term, sort of adhering or gluing two molecules together when they interact through these forces, right? And there's several different types. However, there's only 3 of them that we really care about in OChem, all right? And we're going to go in order of strength of those 3 particular ones. The first one is going to be the hydrogen bond. The second one is dipole-dipole interactions. And the third one is going to be van der Waals forces. You guys may have learned about van der Waals forces under a different name. They're also called London dispersion forces. So, regardless of what you call them, they're basically the same thing. All right, and they are written here in order of strength. Right, hydrogen bonds are the strongest of these 3 intermolecular forces. Dipole-dipoles are in the middle, and van der Waals are the weakest. All right, so let me explain how these work. And again, you've probably seen this before, but it's good to get reviewed. And I'm going to go a little out of order here. I'm actually going to start off with dipole-dipole. All right. So we learned in the last video that whenever you have strong enough partial negatives or partial positives on given atoms, they can come together a lot of times and make a covalent bond, right? That's because they're attracted to each other so much that they want to, permanently share electrons. Now, dipole moments, partial positive, partial negatives, they can also lead to attractions that don't form full covalent bonds. It's more just sort of an interaction, more like a pairing that can be a little bit more easily broken than a full covalent bond. These are dipole-dipole interactions. All right. Let's say we had acetone. Acetone is a ketone that has this structure. All right. Hopefully you can recognize that we would definitely have a dipole moment in this molecule. You'd have a partial negative on the oxygen and a partial positive on the carbon. Okay? Now, let's say another acetone molecule came bopping along. Right? Again, with a partial positive on the carbon and a partial negative on the oxygen. Well, if they get close enough, the partial positive of one acetone molecule can sort of interact with the partial negative of another one, and they can just sort of stick together a bit, right? They can adhere. And these types of interactions would be found through the entire acetone sample. Same thing if we had something like this. Let's say we had an alkyl halide, right? You got a partial negative on the bromine, partial positive on this carbon. Another molecule comes along. Come on, there we go. We could get interactions between this carbon and that Br. We could also get interactions between this carbon and this Br, right? So, those interactions are created because we've created a dipole. All right. So that's dipole-dipole. Next I want to talk about hydrogen bonding, and there was actually a reason I chose to talk about dipole-dipole first. There's a little lag between my input and with the stylus and the appearance on the screen, so it's kind of throwing me off a little bit. Please bear with me. All right. Hydrogen bonding is basically just a specialized type of dipole-dipole. That's why I wanted to talk about that one first. All right. Hydrogen bonding occurs whenever you have a molecule in which H is bonded to fluorine, oxygen, or nitrogen. Okay? So if you have an example like this, let's say we have an alcohol. Okay? Now, of course, you would have a dipole moment between the oxygen and the carbon. But you'd also have a dipole moment between the oxygen and the hydrogen. Okay? So partial negative on the oxygen, partial positive on the carbon, partial positive on the hydrogen. The reason hydrogen bonding is special is because this partial positive on the hydrogen is going to be pretty strong. Stronger than the partial positive on your carbon. Okay? Strong enough that it gets its own special classification. So, for example, if you had another molecule of this alcohol, just like we saw with dipole-dipole, you could have interactions, strong interactions between these partial positives and partial negatives, right? So, again, really the same thing as what we saw with dipole-dipole interactions. It's just a specialized type that makes partially positive hydrogens, which are stronger, which are more strongly partially positive. Wow, that's quite a description. Than carbons are. All right. All right. The third type I'm going to talk about are van der Waals forces. Now, these are the weakest ones. Although, don't be fooled. Even if you only have van der Waals forces present, if you have enough of them, they can be pretty powerful on their own. But individually, they are the weakest ones. All right? Let's just imagine a molecule. Let's say we have, I don't know, pentane. Now, if you look at pentane, I think you can pretty easily see that there's nothing here that's going to give you a true dipole moment, right? There's nothing electronegative to make permanent partial positives or partial negatives. However, don't forget, you do still have the electrons that are present in the form of a cloud. We have the electron cloud, and literally, just like a regular cloud, it can sort of drift back and forth over time. Just lay on the grass and watch the nice fluffy clouds in the sky. Just notice it drifting. That's what happens, all right? So what van der Waals forces are they're very weak, transient dipoles that occur due to drifting of your electron cloud. And I say transient because, it might drift one way for, a period of time, and then it might drift another way. And they're very weak. They're not very strong, all right? Unfortunately, my fat stylus can't really draw this to scale, but I'm trying to draw sort of itty-bitty partial negatives here. So you might have something like this that occurs. The electron cloud in this case has drifted to the left a bit. So we have a slight partial positive on this end of the molecule, slight partial negative on the left side of the molecule, and a slight partial positive over here on the right side. In a few minutes, that might change. They might flip-flop, right? If you have a couple of molecules who happen to line up with their, weak partial positives and negatives aligned, then you can have interactions. All right? all molecules, all organic molecules have van der Waals forces. No matter whether it has an electronegative atom or not. Right? So all organic molecules have van der Waals forces. Some also have dipole interactions. Some also have hydrogen bonding. Some have all three. Just depends on what you happen to have. Right? A really cool example that's in your book, or at least it's in my book. I don't know if it's in your updated edition, but just to show you how effectively these weak van der Waals forces can accumulate. Think of a gecko, right? Gecko or really anything else that can crawl on a wall and not fall down, right? You ever wonder how they stick to the wall? You might think it's a secretion of some sort of glue or adhesive or something. It's actually not that. These creatures have tiny, tiny little hair-like structures on their feet, and these little hair-like structures all have van der Waals forces associated with them. And there's so many of them that they can all interact with van der Waals forces in the wall or tree or whatever surface they're on, and actually there's actually so many of them it can cause them to adhere just from the magnetic properties of these interactions. So that's pretty cool. It's pretty neat. So the next time you see a critter crawling on your wall, hopefully you'll think of van der Waals forces. All right. Well, like I said earlier, the types of intermolecular forces that you have and the magnitude of them, they can affect certain physical properties. All right. Now I'm going to talk about 3 specific physical properties. All right. The first one is going to be boiling point. And you guys know what a boiling point is, right? Temperature at which a liquid transitions into a gas. All right? You ever think about what's actually happening at a molecular level whenever you boil something? I'm sure you have many times. Anyway, I'm going to remind you, though, think about it. What's actually happening whenever you boil a sample of something? Water, for example. Well, you have a bunch of molecules that have a certain level of attraction, and they have a certain level of proximity to each other while in the liquid state, right? And they're attracted to each other to this certain degree by the types of intermolecular forces that they have and the magnitude that they have, right? Whenever you boil something, basically what you're doing is you're inputting enough energy into the system in the form of heat to overcome those attractions, to break them, and so the molecules can spread out, right? In this case, they spread out into the gaseous form. All right. We can associate certain aspects of molecular interactions to trends in boiling point. All right. For one thing, the most important thing when looking at the effects on boiling point, the stronger, I'm going to use IM for intermolecular forces, the stronger intermolecular forces that you have, the higher the boiling point tends to be. Right? So for example, let's say we had this guy and we had this guy, right? They're pretty similar. The big difference is, of course, this one has an OH attached to it. All right? So if you ask yourself what particular intermolecular forces are present, well, the guy on the right, butane, it really only has van der Waals, right? Nothing electronegative, so just van der Waals. The guy on the left has van der Waals, for sure, as everything does. It also has a dipole moment, dipole-dipole interactions between your oxygen and carbon. And you'll also notice we have hydrogen bonding between the oxygen and the hydrogen. And we know that hydrogen bonding is the strongest type of intermolecular force. The other compound doesn't have that. So this guy would have the highest boiling point, right? So that's the first thing you always look for, is what types of intermolecular forces are present. All right, the second thing, and I didn't mean to erase the thing about boiling point, so please forgive me. The second thing to look at is surface area. increased surface area is correlated with increased boiling point. All right. What increases or decreases surface area? Well, it all depends on how flat your molecule is. If you have just a singular chain, right? So this is what? 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. If you have a singular chain that's stretched out, this has a very large surface area. All right, we could take the same 9 carbons and draw something like that. These guys right here are branched chains. They have a main chain with other little branches popping off of it. This reduces the surface area, right? So in general, what we see as a result is that if you have branching occurring, it's going to lower your boiling point. Out of these two compounds, this one on the left would definitely have a higher boiling point. Okay? So all things are equal here. Everything just has van der Waals forces. The one with the higher surface area is definitely going to be your highest boiling point material. Now we could change it. We could tweak it a little bit. We could take that same compound, but instead, let me make that look better. Crud. Well, you know what? Screw it. I'm not going to put it on that carbon. I'll put it on this one. There we go. Let's say we had an OH on this one. This would change things a little bit because the compound on the right now, it has hydrogen bonding and dipole-dipole interactions, while the one on the left does not. So even though the one on the left has a higher surface area, the one on the right would have a higher boiling point. Right? So there is a hierarchy here. The type of intermolecular force is the most important. Surface area is the second most important. That does have its limitations. I mean, if we had something like this versus something like, this. This is a little bit of a gray area because the surface area of the top one is so much bigger than the second one. That is eventually going to overtake the type of intermolecular force. I'm not going to give you any like that, but I just wanted you to know that you eventually would have to come to a point where you would have to make a bit of a judgment call. But for the most part, it's pretty predictable by looking at first the type of forces and then second the surface area. All right. All right. So the next thing we want to talk about is melting point. Melting point, of course, is the temperature at which a solid transitions into a liquid, right? So in this case, you're dealing with, very, very close packed arrangements of atoms, right? So close that they can form a solid structure. You're adding enough energy in the form of heat not to completely separate them into a gas, but to sort of loosen those intermolecular interactions a little bit. All right? Now, the rules that apply for melting point are mostly the same as the rules for boiling point, with one exception. And that has to do with the symmetry of the molecule. More symmetrical arrangements in your compound increase the melting point. So this is really a third aspect you have to look for, right? And really, out of all of these now, symmetry is probably going to be the second most important one to look for melting point. Types of intermolecular forces are most important. symmetry, and then surface area. All right. As an example, let's take a look at a couple of compounds. Let's take a look at pentane versus another compound with the same molecular formula, but a different arrangement. Hey, what's that called? That's called a constitutional isomer. This one's called neopentane. All right, and we can make an interesting look at these. If we look at these, actually, no. Wait a minute. I messed up. That's what we're supposed to have. Sorry about that. All right, so these both have the same molecular formula. However, there's a little bit of a different arrangement. They're both branched compounds, right? Well, if we were looking at this in terms of boiling point, well, they're both branched, but this one is less branched, and it does have a chain with a higher surface area, a continuous 4-carbon chain, whereas the one on the right doesn't. It has a continuous 3-carbon chain. So in this particular case, this one would have the higher boiling point. Okay? However, if you look at these, though, if we look for symmetry, remember, symmetry doesn't matter with boiling point, but it does with melting point. With the compound on the right, we can draw a line of symmetry right there and end up with 2 equivalent halves. All right? More symmetrical molecules can pack together more tightly in a lattice structure, in a solid structure. Doesn't affect their packing in a more liquid arrangement, but it does in a solid arrangement. All right. This guy on the left, it has no symmetry. There are not any lines of symmetry that you can draw through this one, right? So as a result, the one on the left, even though it has a higher boiling point, is not going to have as high of a melting point as the second one. So that's kind of an interesting little quirk of melting point versus boiling point. Again, we could change this a little bit if we were comparing this instead. Then the symmetry would be trumped by this NH2 group that can hydrogen bond. So out of all these, this would have the highest melting point. But to break the tie between the top two, you would look at symmetry first before you would look at surface area. Then you could look at something like this. This is the original one I put up. This is another constitutional isomer, right? Well, again, we can't use type of intermolecular force because they're all just van der Waals, all right? Just like we saw last time, we still have this line of symmetry. But, hey, guess what? We got a line of symmetry in pentane, too. How about that? So in that case, since symmetry is basically equal, then you would use surface area to determine the melting point. This one on the left would have a higher melting point. All right. So, in summary, there's a few different things you want to look at when determining relative boiling points and melting points. Boiling point, first look at the type of forces you have, then look at surface area. For melting point, first look at the type of forces you have, then look at symmetry, then look at surface area. All right. Okay, there's one last thing I want to talk about, and again, this was probably, old hat to you guys, but I want to make sure you know it. That's solubility. All right? Now, of course, you guys have learned the traditional rule of like dissolves like when matching up a solute and solvent. And of course, that refers to the degree of polarity, right? Polar solutes generally dissolve in polar solvents. Non-polar solutes dissolve in non-polar solvents, right? So if we took something like pentane, and let's say we tried to dissolve it in a couple of things, right? First, we tried to dissolve it in water. or we try to dissolve it in carbon tetrachloride, which is CCl4. All right. Now, if we're trying to predict this, what we would want to do is we would want to try to predict the relative polarity of each one of these compounds. There's nothing electronegative at all. There's no dipole moments in pentane, so that one's definitely nonpolar. All right. Water, certainly, I think is well known as being a very polar solvent. Carbon tetrachloride does have individual dipole bonds, but they are symmetrical enough to cancel each other out. So this one is nonpolar as well. As you might expect, pentane would not be soluble in your water, and it would be soluble in your carbon tetrachloride, right? That's exactly what you would expect. Like dissolves like. However, it's not quite always that simple. Let's take acetone again. Acetone we use a crap ton of in the OChem lab. We use it, in fact, we commonly use acetone as our major solvent in the organic lab, not water. All right, I'll explain why. All right, again, let's see if we can dissolve water, or acetone in water or carbon tetrachloride. Well, here are the results. You can definitely dissolve acetone in water. Why? Well, guess what? We have a dipole moment. We got a partially negative on that oxygen. We got a partial positive on this carbon. Dipole moment makes this area of the molecule polar, which makes it happy to dissolve in water. However, guess what? It can also dissolve in carbon tetrachloride. Yeah, I can dissolve in both. Reason being, it's got two CH3 groups on either end of it. These parts of the molecule are nonpolar. So you'll see it's not always just a cut and dried black and white type of situation with polarity of molecules. With organic molecules, a lot of times we have to consider polar parts of the molecule and polar or nonpolar parts. Acetone, in fact, has portions that make it dissolve well in both many polar solvents and nonpolar solvents. For that reason, acetone itself is a very good solvent, and in fact, it's the solvent of choice that we use most of the time in organic chemistry. In fact, you may have heard of water referred to as the universal solvent. I think that is a bunch of BS because, hey, it can't be a universal solvent because it doesn't dissolve nonpolar stuff. I think acetone has a much better claim on that title, but that's just my opinion. All right. Last thing I want to talk about are going to be, actually, take that back. I need to go back to solubility a little bit. All right, one thing I think you guys should be aware of is that there's a general rule for how well organic compounds can dissolve in water. There's a rule of thumb. Generally speaking, for an organic compound to dissolve in water, what you do is you got to look at the ratio of carbons. Come on, I'm just trying to draw a colon here. All right, that's a really crappy colon. Looks like an exclamation point. That'll do. The ratio of carbons to oxygens plus nitrogens in the molecule. All right. It's soluble in water if this ratio is less than or equal to 5. Okay? So if we were to look at something like this. Right? This molecule has 5 carbons, 1 oxygen. This would be water soluble. This one has a ratio of 7 carbons for 1 oxygen. Right? This would be H2O insoluble. This one, ratio to 3 to 1, water soluble. And what a lot of people don't recognize is that there's differing degrees of solubility, right? For example, this guy and this guy are both water soluble. However, this one is more soluble because its ratio is lower, right? So if you tried to dissolve both of these in separate water samples, they would both dissolve, but the one with the NH2 in this case would go faster. It would dissolve faster than the one with the oxygen because the ratio would be much less, right? Now this one over here that says H2O insoluble, let's say I just happen to add, I don't know, an NH2 group or something on there, right? That changes our ratio, right? That changes our carbon to oxygen-nitrogen ratio to 7:2, which reduces to 3.5:1, which is in our limits. So if we did that, then it would give you water solubility, all right? So keep that in mind whenever you're trying to predict whether compounds will be soluble in water or not. Look at the number of carbons they have versus the number of oxygens and nitrogens. All right. Last thing I want to talk about, something called amphipathic compounds. Come on. All right, amphipathic compounds are compounds that have very distinct, very strong polar and nonpolar regions in their structure at the same time, right? We saw that acetone sort of has these properties, but we wouldn't really classify it as being amphipathic because, it doesn't have a really strong polar region. It doesn't have a really strong nonpolar region. Here is a good example of an amphipathic compound. All right, let's say we had this. All right. And if we look at this structure, here we have a group over here. It's got 2 oxygens, one of which is negative. This is very, very polar. Very polar. All right. This group is exclusively hydrocarbons, right? Nothing electronegative. And it's a large chain, so that side is very, very nonpolar. Polar groups, like we said, polar groups like to dissolve in water, right? We refer to them as being water-loving, and there's a name for that. We call that hydrophilic. Nonpolar materials do not like water, so we call them hydrophobic. All right, so amphipathic compounds have distinct hydrophobic and hydrophilic portions within a molecule. And when placed in a particular solvent, they'll arrange themselves in certain alignments as to maximize the optimal interactions that they can have. A classic example of this is soap, right? In fact, the molecule that I just showed you would be a good representative of something that you might find in a soap, right? Soap, if you've ever wondered how it works to get the dirt off your hands, here's how, right? I'm going to use the classic design of circles and squiggles here. All right, this represents a soap molecule or an amphipathic molecule. This is our polar head group, which is hydrophilic. This is our hydrocarbon tail, which is hydrophobic. And both of them are necessary in order to successfully wash your hands. What solvent do you wash your hands with? Water, of course, right? So in order for your soap to interact with water, you need the hydrophilic portions. What's the polarity of common dirts and soils and stuff that you have on your hands? Most of that is actually pretty non-polar, all right? So here's what happens. Let's say you get ready to wash your hands. First thing you do, turn your water on, you wet your hands, right? And then you put soap on and you start lathering. What happens is, let's just say that the empty space off to the side is water, right, surrounding it. All right, what's going to happen is your hydrophilic heads are going to try to align themselves to the water on the outside. At the same time, I'll have to erase this. At the same time, your hydrophobic tails, they want to get away. They don't want to have anything to do with that water. So they're going to sort of arrange themselves like this. Okay? Polar head groups exposed to the water, hydrophobic groups inside. This allows the soap to dissolve in the water, and also when you mix it onto your hands, the nonpolar dirt, what it does is it migrates to the middle into this sort of little hydrophobic pocket that can carry it, and as you rinse the soap off of your hands, everything gets sort of mechanically washed down the drain, including the dirt. Okay? So, pretty cool. This guy right here is an example of something called a micelle. This is a traditional micelle where you have water on the outside, polar head groups on the outside, hydrophobic tails on the inside. So, you know, as you go along, you've probably seen examples of these in your biology classes as well. Let's say you had a nonpolar solvent. Let's say you had carbon tetrachloride sitting over here. Then these groups would align themselves in a different fashion. They would be backwards, right? Your hydrophobic tails would be on the outside, and your polar head groups would be on the inside. This is called a reverse micelle. You see a pattern here, though. The polar groups align themselves with polar solvents and against nonpolar solvents. You can see several other arrangements too. This one's for all you bio majors out there. Alright, you guys should know what this is by now. What is this? This is referred to as a lipid bilayer. And hey, where have you seen that before? Cell membranes. Yeah. Same principle though, using polar and nonpolar ends, hydrophobic, hydrophilic ends, to align in a certain manner. Alright. Well, that basically finishes up Chapter 3. Short one, huh? Alright, go ahead and be working through this, and I will talk to you next time. Goodbye.